Okay, this set of notes deals with motion maps. So let's get started. What are motion maps? You might think I don't know, is it a map? Not quite. Is it a map with motion? Not exactly. Good try. You're not far off, though. So let's get started. Motion maps are a simple representation of an object in motion using vectors, which, if you remember, vectors are just arrows on a graph. They represent position, velocity, and can also represent acceleration, which we'll talk about later. This is what a motion map looks like. But we'll get more on the specifics later. These arrows, they're called velocity vectors. The dot at the end represents 1 second in time, and then the vector represents velocity, or how fast you're going. The longer the vector, the higher the velocity. So in this case, the top arrow, the top vector, would have more velocity than the bottom vector. Those vectors are placed on something like this. It looks a lot like a number line or a timeline, but it tells us its position. And it usually starts at, or it always starts at 0. So now Fritz will sing you a song. Just kidding, this is physics. We don't sing here. So, for example, we'll start with a qualitative motion map. That means exact numerical values will not be necessary. We're not going to use numbers, just the picture. We're going to make this motion map based on a descriptive observation. So we're looking at this position versus time graph. The blue line represents a blue car, and the red line represents a red car. Notice both cars are moving at a constant velocity because both of those lines are straight. The blue car starts at the origin, starts at 0, the position of 0, and is moving to the right. So it starts at 0 meters and it moves to the right. The red car starts further away from the origin and is also moving to the right. Which car was traveling faster? Well, the blue car was, because it covers more distance in the same time. If you look at that, you can see in this first 3 seconds, this blue car had to travel clear from 0 to here. The red car only had to go from here to there. So it didn't cover quite as much distance in that 3 seconds as the blue line did. Also, the slope is steeper for the blue line, and we'll talk about that later too. So the motion map for these two cars would look something like this. We'd start here at 0, and the blue line, the blue car started at 0 meters, so its first arrow is going to start there, and then it's got some pretty long vectors. The red car did not start at 0, it started a little after 0, so we're going to start at a little after 0. And it didn't go as fast, so its vectors are shorter. So that's just a qualitative example. If you were to see this map, you would automatically assume that the blue car was going faster and that it started at a spot closer to the origin than the red car. So let's move on to the real deal with quantitative motion maps. That means numbers. Dun, dun, dun. Okay, so look at this position time graph for a really confused and bipolar cat. The cat starts off 2 meters away from his litter box, which we're going to call the origin. Okay. Then imagine that cat 2 meters away from his litter box. He's going to start running a little bit to go next door to say hi to his friend, Perry the platypus. Notice here in that part of the graph, he goes 1, 2, 3, 4 meters in 1, 2 seconds. So that would be 2 meters per second. He stays there for a second and then turns back around and just kind of strolls to his comfy little bed. Notice that he went 1, 2, 3 meters in 1, 2, 3 seconds. So instead of 2 meters per second this time, he's going half the speed at 1 meter per second. And then he has a nap for a couple seconds. So if we start drawing that graph, we're going to start, the initial position of the cat was at 2 meters. So we're going to put a dot at 2 meters. That represents the first second. In the first second, since he was going 2 meters per second, we're going to go for 2 meters on that arrow. And then on the second second, which would be this dot, he goes 2 more meters. So the arrows here would be 2 meters long. And then when he gets to gets all the way to the platypus's house, he just rests for a second. So we're going to put a dot here with no arrow because he's not moving. It just represents that a second has passed without movement. Okay. So he starts to move back in the other direction. And since he's no longer going farther away from the origin, he's going back closer to the 0, right? He's going from here down to here. We're going to drop down a line and put a dot. So we have the first second, the second second, the third second he rests, the fourth second here at 4, he starts to go back. Oh, the first one's 0, sorry. So 0 to 1, 1 to 2, 2 to 3, and this starts at 3. So here on the graph at 3, he starts to go back, and remember we said he went 1 meter per second. So we're going to draw arrows. Oh, sorry. We're going to draw arrows that go back for 1 meter per second. So 1, and then the next second he goes another 1, and the next second he goes another 1. And then he has nap time, so we would draw another dot there. And then that was 2 more seconds of nap time. So we're just going to put 2 more seconds without movement, no vectors, underneath that last one. And that's it. That's all you have to do.